See, bromination of alkanes is the same as chlorination. Then it's iodination. Iodination is little interesting. You know, fluorination is fast, occurs with explosive speed, whereas iodination is slow. At the same time, it is reversible. I mean, even the backward reaction occurs. Let me show you. See, methane reacts with iodine to form methyl iodide, that too on heating. You get hydrogen iodide. But the point is, you got reversible reaction in this, reverse reaction also in this. So to prevent the reverse reaction, oxidizing agents like iodic acid, nitric acid, or even mercuric oxide are used. The role of these oxidizing agents is they oxidize Hi into iodine. Let me give you the reaction. See, HiO3 reacts with Hi to form 3I2 along with that water. So this is very interesting. Reaction is slow, so is reversible. And to prevent the reverse reaction, we go for oxidizing agents. Now the overall thing is, let me give you the important note. Overall, if you consider the reactivity of alkanes towards halogen, of course, it has to be the same halogen. Now we know that this reaction follows free radical mechanism. So therefore, it is this. Because this is the order in which the stability of the free radicals decreases, right? Now, if you consider the reactivity order of halogens, towards the same alkane, of course, a discussed one. We know that fluorine is most reactive. Iodine is least reactive. Okay, so let me write that this is in fact the order of stability of the free radicals, right? Okay. Now let us take the very important topic, wherein we will be discussing the number of products obtained on monohalogenation. And even their percentage yields. Okay. Now let us start with what is monohalogenation. It is just the replacement of one of the hydrogen atoms by halogen atom. Let us take methane to start with. Consider methane. How many different types of monohalogenation products do we get? We get just one variety because there is only one type of carbon atom. Okay, so we get methyl chloride. Now, what if ethane is taken? Look at the thing. You have to be a little careful. Now, both are in the same environment. All 6 hydrogens are in the same environment. Any of these hydrogens, when replaced, are going to give you the same product. That means the product will have the same IUPAC name. Remember, to avoid confusion, it is better to take the IUPAC name of the product that is written. Otherwise, sometimes we take the same product for twice or thrice also. Now, with chlorine, yes, we get just one variety. Ethyl chloride. All 6 hydrogens, any of these 6 hydrogens which are in the same environment, when replaced by a halogen atom, will give you just one product, that is ethyl chloride. So here you got just one product. Even in this case also you got one product. Now let us take propane. Yes. Now the interesting thing begins. See, here you got these two in the same environment. I mean the 6 hydrogens are in the same environment. Now when you replace, you substitute any of these 6 hydrogen atoms, you will get one chloropropane, or let me say N-propyl chloride. Let me write that this is a product what we get when hydrogens marked with this symbol are subjected to monohalogenation. Now let me mark this in a different way. Because these 2 hydrogens are in a different environment. When any of these hydrogens is replaced by a halogen atom, we get isopropyl chloride, or you can say 2-chloropropane. You need to be very cautious. So this is the product what we get when this particular thing is replaced. I mean, the hydrogens attached to the second carbon are replaced. Okay. So let me tell you very clearly that here we get two products, two different types of products. But when you consider the second one, of course, in the first one, we don't have any asymmetric or chiral center. Even in the second one, do we have any asymmetric or chiral center? No, we don't have. So you can say two products or even two isomers also. Okay, we'll give you a very interesting thing, taking butane. I mean N-butane. Let us go for that. Now check this out. Now when N-butane is subjected to monohalogenation, look at this. Let us write them this way. Now these six are in the same environment. The six hydrogens are in the same environment. So when you replace any of these hydrogens by chlorine, you get the same product. That is, okay, let me write the product. So this is N-butyl chloride, or the IUPAC name is 1-chlorobutane. Okay. Now check out the substrate or the reactant again. These two are in the same environment, right? These two are in the same environment. So we are going to get this product when any of those hydrogens is replaced by chlorine. That is 2-chlorobutane. Nothing but secondary butyl chloride. Okay. Now, see, in the first one, we don't have any chiral center, but in the second one, there is a chiral center. You need to be very cautious when you go for something with a chiral center. I can give you many different points here. Okay, let me tell you that here in this case, we get a total of course, two products, but three isomers. Because in this case, we get D and L. That means a pair of enantiomers. Okay, you got one asymmetric center. So one enantiomeric pair. You have to be very careful. I can give you any number of questions. One enantiomeric pair, that is DL. Now, one more thing. Number of fractions collected on fractional distillation. It is only two again. Because, you know, fractional distillation is a process based on The differences in boiling point. It can separate the substances or the compounds into fractions only if they differ in their boiling point. But because the D and L differ only in the rotation of plane polarized light, but not in boiling point, they cannot be obtained in the form of two different fractions. We get both in the form of just one fraction. D and L differ only in the rotation of plane polarized light, but not in boiling point. So this is very interesting. Total number of monohalogenation products. Sometimes they give structural. The answer is 2. Number of isomers, 3. Number of enantiomeric pairs, 1. And the number of fractions collected, 2. So these are the different types of questions that can be asked. Okay. Now in continuation to this, we calculate the percentages also. The percentage of N-butyl chloride and the secondary butyl chloride. But before that, let me tell you one more interesting thing. Now, in order to know the percentage yield, we need to know two things: reactivity and selectivity. You know, reactivity and selectivity are inversely proportional to each other. Greater the reactivity, lesser is the selectivity. Of course, we know that the reactivity order of halogen follows this order, right? We know that the reaction with fluorine is explosive and with iodine is very slow. Let us discuss about these two now, taking those two into consideration. Now coming to the reactivity, chlorine is more reactive when compared to bromine. So if you consider selectivity, then exactly opposite. Chlorine is less selective when compared to bromine. How can we say that? Yes. Let us see the ratio of different types of hydrogens abstracted when chlorine is used. It follows this: 1:3.8:5. You need to remember this. That means a 3-degree hydrogen is replaced 5 times more when compared to a 1-degree hydrogen. Means the abstraction of a 3-degree hydrogen is 5 times when compared to 1-degree hydrogen. Because when you go for the abstraction of a 3-degree hydrogen, you are going to get a 3-degree free radical, which is a more stable one when compared to 1-degree one. So is the ratio. Now, check this out. With bromine, it is 1 is to 82 is to 1600. See this, very interesting. Bromine is less reactive, more selective. Compare these two. See, the abstraction of a 3-degree hydrogen by bromine is about 1600 times than what it is with a 1-degree hydrogen. Much more when compared to chlorine, right? Which is only 5 times when compared to 1 degree in case of chlorination. Bromine is less reactive, so is more selective. Selectively abstracting the 3-degree hydrogen. So you need to actually remember these ratios. Let me calculate the percentages of N-butyl chloride and isobutyl chloride taking this ratio into consideration. Now percentage yield of N-butyl chloride. Okay, for convenience sake, let me again write N-butane. Now, these two, of course, are in the same environment. They are of 1 degree type. You got 6 1-degree hydrogens. Now, these two are in the same environment. They are of 2 degree type. Now, see, N-butyl chloride is obtained when the hydrogens of 1 degree type are replaced by halogen atoms. Let us take the percentage yield. We got 6 such hydrogens of 1 degree type into the reactivity. Okay, so this is the number of hydrogens of that type, and this is the reactivity of that type of hydrogen atom. Then divided by the total. Again, the same 6 into 1 plus we got 4 hydrogens of 2 degree type, a different type, multiplied by 3.8 into 100 percentage. So how much do we get? 6 by 6 plus okay, 6 by 6 plus 15.2 into 100. This is 6 by 21.2 into 100. It's almost equal to 25 is 100, 5 into 6 is 30. So it will be roughly 29%. I remember the percentage. So the percentage yield of N-butyl chloride is 29%. Now, the percentage yield of the other one, that is a secondary butyl chloride. Of course, it is 100 minus 29, 71%. Or else you can calculate. Or you can calculate this way. It's by total 4 into 3.8 by the total thing 6 into 1 plus 4 into 3.8 into 100. So this is 71%. So this is how we can calculate the percentage yields of different isomers octane. Okay. Many different types of questions are asked in the previous